Oh. Let me start with 1.5. Solution set of linear systems. Oh, solution set. Okay. Mm, we're talking about the matrix equation, right? AX equals B. So that's a matrix form of the linear system of linear equations. Um, but here, first one, let me consider the matrix equation with um, zero column vector on the right-hand side. So in that case, we say that the linear system is homogeneous. So here's definition. So a linear system uh, called homogeneous. So homogeneous means if it can be written as, I mean, the matrix equation. I mean, the system, linear systems can be written as AX equal to 0. Okay. So here's a fact. The first one, AX 0 equals 0 always has trivial solution. So it always has trivial solution. The trivial means this obvious solution, which is 0, right? So AX equals 0. What's the solution of this equation? 0. 0 vector. If x equals 0 vector, then what? This equation says 5. So 0 vector is the solution, and then this is a trivial solution. Okay. So we're not interested in trivial solution. What we are interested in is a non-trivial solution, which is non-zero solution vector. Okay. Trivial solution, x bar is equal to 0. So non-trivial solution is a solution, I mean, is a non-zero. Let me just say let me make it crystal clear. A solution small is equal to 0. It's not equal to 0. Okay. So maybe, a sum of entry could be 0, right? Okay. That doesn't mean that every single entry in an X is equal to 0. No. Okay, that does not mean. Homogeneous system is always consistent. Why? Because trivial solution. Okay. So the homogeneous system and it's the one solution, right? Trivial solution. That's why the homogeneous system is always consistent. Okay. Third one, homogeneous system has a non-trivial solution if and only if the system has at least one free variable. A homogeneous has a non-trivial solution if and only if. Okay. Sometimes we write it as IFF, stand for if and only if. Okay. The system has at least one free variable. Okay. So that's the Abide theorem 2. Okay, so just search the theorem 2 in textbook. Okay, so it has one free variable. What does that mean here? There are a lot of meaning in here. We can find out. And it's the one free variable. What kind of circumstance are we gonna get the free variable? So what it means for a free variable means that at least the one column is not a pivot column. So here's the example, not example exactly, but so think about 3 by 3 matrix in the homogeneous systems. So let's say third column is not a pivot column. Then reducing the row echelon form. Then so we got this. Yeah, so REF, okay, not just EF. Just assume that we reduce echelon form REF. Okay, so we got this, and then let's say A33 equals 0. That's what that means, right? So third column is not a pivot column. Then applying this one to the homogeneous system, that means the row is simply 0 row. So x3 could be any number, any non-zero number, right? So x3 must be a free variable. So this system has non-trivial solution. Okay. So so system has at least one free variable if and only if the system has non-trivial solution. Okay. So let's see example 1 in a textbook. So let's see example 2 in the textbook 1.5. Example 2. So the question is this: a single linear equation can be treated as a very simple system of equations. Describe all solutions of homogeneous system. Okay. So 10x1, so 10x1, minus 3x2, minus 2x3 equals 0. Okay. So to find out the description of the solution set of that homogeneous, so this is a homogeneous system. So let's see. We need to figure out the free variable, right? First one. But I'm sure that the x2 and x3 are free variable. Okay, because x1 can be expressed as x2 and x3. You can just express this one as a matrix system, a homogeneous system, right? Like this. Then what does A look like? A must be, 10, right? And then -3 and -2 and then 0, 0, 0. Okay, now 0, 0, 0, right? So you see that here, the first column is pivot column, right? Because this is a pivot position. How can you figure out that this is a pivot position? Because if you just reduce echelon form, reduce this matrix to echelon form, then you're gonna get what? 10 and -3, -2, and then 0, 0, 0, and then 0, 0. It's actually, you don't have to anything. That's the echelon form itself, right? And then what? Leading entry in the first row is non-zero. That's why the first column is pivot column. Now then what? The second column is non-pivot column because what? This guy is 0, and then see, this guy is 0. That's why second, third column is non-pivot columns. So then what? X2, x3 must be free variables. So yeah, so you can say that, okay, but without doing that, it's easy to figure out that x2, x3 or pivot free variable, right? So then x1 is see, let me just, oops. So x1 must be what? Is 0.3 x2 and then plus 0.2 x3, right? So I just moved two terms to the right-hand side and divide by 10. So we got this. And then let me express this one in as a parametric vector form. Okay. So x4 is equal to x1, x2, x3 is equal to, okay, so 0.3 x2 plus 0.2 x3. And then here x2 and x3, right? So that is equal to, I'm just, what I'm doing is to write the solution set to rewrite the x bar as parametric vector form, so we can figure out the description of the solution set. So this is going to be 0.3 and then x2, 3x, oops, sorry, x2 times 0.3 and then 1 and 0, right? And then plus x3 times 0.2 and then 0 and 1. Okay. So let's say this is vector u. Say this is vector u. So this is vector v. Okay. Right. Then x bar, any, I mean, solution set can be obtained by vector u and v for any value for x2, and x3. So solution set gonna be this. Set is gonna be the set. We use set notation. Okay. The x bar, I mean x bar, such that x bar is equal to x2 times vector u plus x3 times vector v, and then x2 and x3 is in the set of real number. Okay, that's well, this is a kind of classical way to express solution set, but we learned the span, right? So in now we're not gonna express solution set like this. That's kind of old-fashioned way, because we learned the span, right? This is equal to actually what? Span, right? Vector u and vector v. Because x2 and x3 can be any real number. So what does that mean, span? This is what? The set spanned by, generated by vector u and v, right? Okay, so vector u, let's say vector u is right there. Think about, 3D, three-dimensional space. Right here, and this one, here. Okay, so let's say this is x1, this is x2, here's x3. And so let's say vector u is I don't know, maybe I don't know, maybe like this. Okay, it should be on a x1 x2 plane, right? Because x3 equals 0. So this vector must be on the x1 x2 plane. Okay, this is vector u. This is on the what, x1 x3 plane. Ooh, okay, so maybe like this right here. This is vector v, right? So the span of u and v is what? This must be plane generated by u and v, right? So maybe it's hard to illustrate the plane. Maybe plane like this, okay? Like this. So the x bar solution set is that plane. Any vector on the plane must be solution of that homogeneous system. I mean, this equation. Okay, you bring the vector. Okay, so arbitrarily, just this. Okay, let's say this is definitely. I mean, let's say this is a vector is on that plane. Okay, then put this one into that equation. Then what? That equal sign must be satisfied, which means that that vector is what? Solution of this equation. Okay. So likewise, we wanna from here we can figure out or sometimes visualize the solution set of the system. All right. So let's see. Let's move on. Okay. So let's see example in parametric vector form. Okay. So yeah, I just uh, the I already just use the parametric vector form to get the this one, right, in these problems. But for whom you are not familiar with the parametric vector form, let me give one example for parametric vector form. So what we're gonna do, what we are doing is this. What we first one introduce the homogeneous system, right? Homogeneous system. Okay, check. And the next one, I'll give one simple example for parametric vector form. Okay, for whom don't get it so far. Okay, so let's see homogeneous system. Okay, so example 1 and 3 and -5 and a 1, 4, -8 and then -3, -7 and 9 and then oops 0, 0, 0. Okay, so this is homogeneous system. All right, so let's find our solution set. What are you gonna do? We do REF, right? Okay, or EF. REF, EF doesn't matter. Okay, let me just say EF. Okay, echelon form. But in textbook, maybe they say REF. That means a reduced echelon form. I mean, a raw echelon form. Okay. Uh, then we're gonna get 1. Okay. Sorry, let me get the REF. Reduced raw echelon form. 1, 0, and 4, 0, 1, -3, 0, 0, 0, and 0, 0, 0. Okay. I use three elementary operations. Sure that. So what does that mean? It means that x1 is what? -4 times x3, and the x2 is equal to 3x3, and the x3 is free, right? So which means that x1 is equal to -4 times x3, and the x2 is equal to 3 times x3, and the x3 is free. Okay. So expressing the solution as a vector form, x1, x2, x3 is going to be now express x1, x2 in terms of free variable. I think that's the key to get the parametric vector form of the solution set. Okay, so to express every single vector, the variable in terms of free variable. Okay, so this will be -4 x3, 3 times x3, and then free, which is x3. So this is going to be x3 times -4, 3, 1. Okay, so you can see that what the solution set going to be what? It's going to be the actually not plane, but just a line spanned by what? -4, 3, and 1, right? Isn't it? Okay. So, but this vector is in three-dimensional space. So solution set is what? Line, but in three-dimensional space. So here's x1, x2, and x3. And then yeah, maybe let's see, 1, 3, -4, maybe like this. Okay, this is a vector. Let's say this vector W. Okay, so W is this, and then the line contain in that direction W. That's going to be solution set. Okay, that's going to be solution set. That's a solution set. Okay. Solution set. Okay. Right. So that's the parametric vector form of the solution. Okay. Think about the non-homogeneous system. Next one, non-homogeneous system. The one, I mean, this is 2, 1. This is a homogeneous system. And 2 hyphen 2 is non-homogeneous parametric vector form of the non-homogeneous system. Okay. So definition. Non-homogeneous system has what? AX is equal to B, and the B is not a zero vector. Okay. That's the non-homogeneous system. So here's a fact. So we're going to use a superposition principle. What is superposition principle? Let me just write down, finish writing the fact. If a non-homogeneous system has many solutions, We're talking about the parametric vector form. What circumstance we're going to have parametric vector form? If the system has free variable, right? That means the system has infinitely many solutions, right? So if one system has many solutions, then we can write the solution set as a parametric vector form because it has free variable. Okay, then the general solution can be written in parametric vector form as this. S is equal to S times the vector P plus T times vector H. Okay, right here. And then S and T are parameters. Okay. We see two parameters involved in a solutions, non-homogeneous systems. Okay. So actually, each term has meaning. One is from the parameter from the homogeneous systems, and then the other one from the particular solution. Let's talk about this. The example. That's the example 3 in textbook. So let's say A is the 3 and the negative 3 and 6 and the 5, negative 2 and 1, negative 4, 4, 8. And vector B is 7, negative 1, and negative 4. Okay. All right, so as you can see that, okay, we got non-homogeneous system. What are we going to do? Yeah, we should get EF or REF, right? So using elementary row operations, next A going to be 1, 0, and then negative 4 over 3, and 0, 0, and 1, and 0, and a 0, 0. Oop. Yeah. Oh, it's negative 8. Thank you. This is right. Mhm. You see, 0, 0, 0, 8, 0, okay? In augmented matrix, third row is 0 row. So, well, third column is not a pivot column, so matrix A is free variable, right? So now that means x1, x2, x3. This is equal to what? It's gonna be, because x1 is what? Negative 1, and then a plus 4 third x3, right? So this is gonna be negative 1 and a plus 4 third and the x3. And then x2 is gonna be just 2, right? 2, and then here is x3 is what? Just x3. I mean 0 plus x3. Sometimes you can say that. So now this is equal to, so we can separate this one as constant vector plus a vector of x3, right? So negative 1 and 2, 0, and a plus and a x3 times 4 third, and then 0 and 1. So you can see that we got two vectors. The first one from the is the solution when x3 equals 0. Think about this. When x3 equals 0, x3 can be any real number, right? This is the parameters, right? Isn't it? This is parameters. So now then when x3 equals 0, then what? The solution must be negative 1, 2, 0. But when x equals 3 equals so here 3 equals 0. When x3 equals 0, sorry. So we got this one. And then when x3 is not equal to 0, we're going to get the whole thing. But anyway, so we can we could describe the solution as the sum of the two vectors. Let's say this is a P. Okay, let's say this is H. Right. Okay. So why just say P? Because this is actually a particular solution. Why this is a particular solution? I told you, when x is 3 equals 0, we're going to get p, right? So that's why this is called a particular solution. In particular, we substitute a specific number, which is 0 into x3, and then we get this one, right? So this one is obtained by when x3 equals 0 in particular. So that's why this is a particular solution. Okay. Next one, why this is called the H? Because this is actually what? The solution of the homogeneous system. We see. So, let me say first one. Okay. When x equals 3, x3 equals 0. Okay. Then ax is equal to ap, right? So if you compute this one, you're going to get actually b. Yeah, that makes sense. It should be. You should get the vector b when you compute ap. Okay. So now this is p is a particular solution. Of non-homogeneous system. Okay. The second one, um, what if x is h? Okay. Right. So here's a then ax, I mean ah is gonna be actually you're gonna get 0. Okay. Can you see that why we got 0? How come? Yeah, you just compute the ah, do matrix multiplication of a and h. Yeah, algebraically it's it's understandable. Okay, it's understandable. There is no problem to understand this. Ah equals 0. Well, how we got the solution of homogeneous system? You see, we got 0. That means what? H is a solution of homogeneous system. Why? Why we got the? Because we didn't solve the homogeneous system. But we solved the non-homogeneous system. But it ended up with what? The end up with the solution involved homogeneous solution of homogeneous system. How? Because you see that here, -1, 2, 0, that was exactly same as vector the vector v after REF, right? So this is the vector after reducing echelon form of vector b, right? So pretty much we split out this one into two vector, and then this one of the that one, right? Makes sense. So when you take out all the numbers, which is corresponding to this one, then we only get this one. That must be what? That when you multiply this one by the matrix A, it should reduce to 0. Otherwise, we're gonna get big trouble because -1 to 0 from this one. This is exactly the same as this one. When you take out that one, the left the what all entries except for this one must produce the 0 when you multiply this one by matrix A. Okay. So okay, so now then a so that means H is a solution of homogeneous system. So now for the non-homogeneous system, and then assuming that that system has many solutions, then matrix the solution set can be expressed as some particular solution and solution of a homogeneous system. Okay, that is called the superposition principle. This is called the superposition principle means that solution can be expressed as a sum of two, can be decomposed into two terms, two parts. One part is the particular solution, the another one is solution of homogeneous system. That's a superposition principle. So, and then here's a question now. So how can you describe the solution set of AXP in R3 geometrically? I mean, so you may just wonder that, okay, so where is S go? Yeah, in this particular problem, yeah, there is only one parameters. Sometimes, but in general, we can write the solution of the non-homogeneous system as like this. Okay, in that sometimes a non-homogeneous system has multiple the free variable, then we may have to write this one as like this. Okay, so how can we describe the solution set of AX is equal to B non-homogeneous system in R3 geometrically? Okay. So X is equal to P plus X3H. Okay, that's what we got so far, right? So then, so this is the question for the example, okay? It's continuously. Let me draw the Cartesian coordinate system. Right? So this is x1, this is x2, and this is x3. Right. So P is what? Negative 1 to 0, right? So it should be on the x1, x2 plane. Right? You see? Negative 2 minus 1, 0. Okay. But mm, hold on a second. Let me say this is x3. This is x1. This is x2. Okay. So I changed the axis, index of axis. Then P, particular solution, must be like this. That's a P. Okay. And then H is what? 4.01, right? 4.01, x1, x2, maybe uh, mm, maybe like this, but not exactly. Okay, this is H. Okay, all right. But the solution set X is what? Is a P plus, and then T. Let me use a T, letter T instead of X3, okay? To emphasize this is parameters. Then P plus H gonna be what? Using the parallelogram rule, P plus H gonna be this, right? Use the color, maybe yellow. Okay, that's the P plus H. Okay. And then, this is a solution when t equals 1. What if t equals 2 and 3? It's possible, right? So for any choice of t, x must be a solution. So to figure out the general form of the solution set in geometrically, let me plug in a couple of specific number into t. When t equals 1, we got this p plus h. When t equals 2, then what? We're going to get 2 times h. Right? So you see, right here. So this is maybe 2 times h. 3 times h is this. Okay, 3 times h. Okay, then we do this p plus h, p plus 2h, p plus 3h. Just keep doing that. Oh, okay, so we see like this right here. Oh, I think this is yep. Here. Okay, p and p plus h. This is right. Okay, I was confused. So we're gonna get p plus h, and then So we got this, and then we're gonna get that, and then we're gonna get this. Okay. Then finally, we'll get what? Finally, we got this one. You see, like this one. I. So that's the I mean, just a point, collect. I mean, collecting all the terminal point of the vector p plus h, p plus 2h. So we got this one. This point, that's going to be end point of p plus h. And then this is going to be end point of p plus 2h. This is p plus 3h, and so on. Okay, so that's a particular solution. This is solution corresponding to homogeneous system. Okay, and then this is a solution set, geometrical expression of the solution set of a non-homogeneous system. As you can see that the solution set of non-homogeneous system is a parallel to solution set of homogeneous system actually. So two lines are parallel. The only different thing, the only gap between them is a particular solution. So when you find a non-homogeneous system having the free variable, you need to find a particular solution and homogeneous system, a solution to homogeneous system. Okay, and then they are parallel. Okay, that's the yeah. So line through P parallel to the solution set of X. So this is the that is the line, the solution set of AX is equal B is a line through P particular solution, and then parallel. That means a parallel. This is symbol of parallel to the solution set of homogeneous system. Okay. So here's theorem 6. Theorem 6. Okay, so look at textbook. Okay, suppose AXB is a consistent for some given vector B. Let's say P be a solution. Then the solution set of a non-homogeneous system is a set of all vectors of the form P plus VH, where VH is any solution of non-homogeneous equations. Okay, so that's the theorem 6. Okay, so just look at that's what I have told. Okay.